Hello, everyone. I'm Namita Jaspal, and here I'm going to talk about uses and importance of water in the field of art conservation. This discussion is more important if we, as responsible beings, want to look for greener and safe treatment material in our lab. And Now, this topic is actually too vast and would need a series of webinars. Today's live session is an attempt to begin a discussion. Here, I would like to now share my presentation. Let's see if it works. So, talking about use of water in art conservation, I would like to discuss a few case studies where we found that the usual solvents that we were using in our lab were not that effective, and nothing was working, but a simple modification of water worked like magic. Though it is not just the cleaning process that utilizes water, we use water for flattening fabric or paper. We use water or water-based gels in treating stains and tide lines. But here in this particular presentation, I'll just talk about the cleaning process and how water can be a powerful tool in cleaning of grime, aged grime, and oxidized varnish. Though I have already discussed a lot about the use of water in paper conservation in my other webinars, um, I'll be taking mainly the canvas paintings and the wall paintings this time. More discussion would be on the canvas paintings. First example is this one. When this painting came to our lab, it was like an easy task. We thought that it is an easy task of just removing the yellowed varnish. Though we could find that there were some very prominent thick strokes of thick varnish in the middle area. And the varnish was not evenly applied on this painting. And therefore, the cracks were more prominent in the area which was thickly varnished. You can see in this picture on the bottom right. So while starting the cleaning process, we thought of first removing the grime, and we tried water, ethanol water mixture, and all the usual things that we do. But it was very surprising. It was good because it's a long time back, it's a decade back, and as we were just, I had mostly the young conservators working with me, and it was really nice experience when we tried and adjusted water, and the weight came out, and the amount of grime that was removed with simple cleaning with the swab was amazing. So let's see if I can show in the video. So here there's a small area that I've just dry cleaned with the dry cleaning sponge. You can see a lot of dirt came out on the sponge also, though we had already cleaned with a soft brush. Then we applied and adjusted water. We adjust because for grime, we have observed that a little rise in pH works very well. So this is basically, we have made the water a little basic. And you can see on the swab stick, large amount of grime, which was on the first look, we didn't realize that it has such thick and aged grime. So you can see the blackened tip of the cotton swab. And after this, the removal of acetone became easier. Removal of varnish with the help of acetone became easier. I think I have really um, lost some of my control because of all the delay in this session. This was then we also removed the varnish with the help of acetone, and you can see the three areas here. The grime is there. Here it's just yellowed varnish, and here it's the clean paint layer, though it is still having a little bit of varnish in the grooves. That was an easy case, a normal, usual kind of work that we do. But in this particular painting, nothing was working. After dry cleaning and cleaning with ethanol water and all to remove the grime, and then trying some organic solvents to remove the darkened varnish, we could easily see the thick and yellowed and brown varnish over the paint layer. And moreover, the complication was also because of a lot of flaking. The paint layer had been almost completely removed. Let's see, I'll take a pen from this area and many other areas. So it was in a very delicate situation, more so because the support was not canvas. It was not a fine fabric. It was a rough kind of fabric, which is used for making furniture and all. But the painting was beautiful, and it was very important also. So we just tried to use water again, just by raising a little pH and adding surfactant, you can say. And it worked like magic. Though it wasn't very fast, it was a slow process. And it took a lot of time. And though we also modified it to form a gel kind of thing so that it stays at a place for longer time. But it was like magic, because earlier we had tried everything, all the organic solvents, the usual things that we do, but it wasn't getting cleaned. You can see this picture in which you'll find that rest of the area is also a bit more cleaner than the left picture, as we were trying different things in different patches. And you can see another area, much more cleaned area in the center, the square area. And this made us think. At that time, I had not read much, though I had read a lot about the modular cleaning program, and but I had not studied that much about it. I have been trying to learn more about it since last, say, I think 4 years. And though I had installed it and had tried to work on it, and maybe that was at the back of my mind, maybe something I had read or something. So this is really amazing that when nothing was working, all the usual solvents and cleansing agents that we had in the lab or whatever we were taught were not working, this modification of water worked. And again, we were introduced to this concept of gelling by the modular cleaning program. And I had a book by Richard Barber, and though I hadn't read it so thoroughly, it was a little difficult for me at that time, but I was picking up certain concepts. And because I wanted to do biotechnology at one point in my life, so these things were quite familiar to me. So this is another example where water, which is supposed to be mild solvent, a weak kind of, say, acid or base, is doing a wonderful job, which none of the mixtures or solvents could do. So here we had used water, triethanolamine, and it had been adjusted to a pH 8.5, and then we had added triton, and we also then tried, because it was taking a little time, so we tried to gel it. Oh, this is the before and after of the earlier picture. Now, this particular painting is another example where water helped. It wasn't varnished that thickly, and it had many areas where there was a white haze kind of thing. Initially, I thought it is blanching, but I realized it is not because of varnish and the moisture trapped underneath. Rather, it is because of some other thing, and we could connect it to these sort of stains. There were many more in the other areas. This particular stain is in this area. It is the back of this area. So it's a life-size painting, and it had these sort of strong, very dark tide lines, and it seemed that something had been maybe accidentally poured over this painting, which had caused these kind of stains. Something was spilled, or somehow there was some liquid associated with it. And maybe the reason of that white haze was the components of that liquid. This is the complete back, so you can see other areas also. They're badly stained with tide lines and all. And it took a lot of time, but we managed to clean the back first, because we thought that the damage to the front was actually coming from the back. So it was very thoroughly cleaned. And again, we use different techniques. And here, it is interesting. I haven't added those pictures, but we used agarose to remove the tide lines. I'll try to show you the pictures maybe alongside, but maybe after this presentation, how we use agarose. Again, it is a gel, water-based gel. And it was very effectively, it not just removed the tide lines, it picked up a lot of acidity. And we found the canvas much more clean after that treatment. And it wasn't just the agarose gel treatment that we did at the back. We also used modified water, adjusted water in certain areas where we found that it is more than just a tide line. So in this painting, I don't have more pictures right now of this painting, I would like to show you after the presentation. It has come out very well. So the white haze was sorted out. So here in this painting, water was the main material that we used for all the processes in cleaning. And it wasn't just a one kind of cleaning. We used agarose gel, we used adjusted water. And apart from that, we also used an adjusted water with chelating agent, EDTA. For the white haze in the front, this particular thing. And this is not just in this area, it is just that in this area it is more prominent. It is, if you see carefully, it is in the left, top left area also. So this whole area had this kind of haze. And moreover, there were some more stains, and they had been treated earlier. There were some retouchings, though there was, I think there was a proper conservation treatment done many years back on this painting because there was a patch also. So this painting also was cleaned mainly by various kinds of modifications of water. This is an example of a wall painting, and though we won't have enough time today, it was already late, but I would like to discuss more things, more examples of actual frescoes and temperas that we have worked on, and how we found a very difficult and tough kind of grime in certain monuments and how we dealt with it. This is, I've just taken one example over here. This is a wall painting, but it is an oil medium. And again, the problem is mainly of the grime. It is 100-year-old temple. And first, when we tried, we did all the tests, usual tests, because we thought maybe there is, because we could see certain shiny strokes on the painting. So we felt that there is some surface layer of varnish or something like that. And we might be able to clean the painting with just using some organic solvent like acetone. Once the varnish is removed, it will take away the grime also. But again, nothing was working. The best thing that we could do was just increasing the pH to some extent. And it worked wonders. And though it just took a lot of, this is just the adjusted water with a raised pH. What is being done right now, the cleaning that is being done right now. But even after this, when we saw these paintings again, we found that there is little grime in the texture of the paint after this cleaning treatment also. So we had modified this adjusted water further by adding a surfactant and then clean the paintings further. And another interesting thing that we realized was that because we had put a facing on these paintings, they were flaking badly. So we had initially put a facing on many of these paintings, which were flaking off, and they were getting cleaned faster as compared to those which were not given any facing. So we felt, and the facing was given with CMC, carboxymethylcellulose. So we thought that maybe that kind of effect, like the way the gels give an effect of keeping the adjusted water a little longer in an area, was doing this kind of wonder of increasing the speed of the cleaning process. So this painting was also given a facing initially, so it is being cleaned in much easier way with just a little pH raised water. We had raised the pH with triethanolamine, which was adjusted to the pH of 8.5. And then again, for the further cleaning, we had added triton. Apart from this cleaning, of course, paper, we won't be talking much about paper in this today's live session, but I would just like to mention how we clean the paper also by various aqueous methods. So we have an immersion technique where we immerse the paper in water, adjusted water or deionized water, depending on the requirement, whether we want to take out the ions from the stubborn grime from the water, or we want to keep it there. We can keep some of the ions over there, and we can do the float washing, blotter washing. We can also do the what we say, what we call slant wash, and another one is a very less aggressive. This is the spot cleaning with gels like agarose, gallon gum, xanthan gum. So such localized treatments can also be given. In all these treatments, it is water which is acting as a solvent for a lot of materials in the grime. And it is also dissolving the acidic components in paper. So this is an example of float washing. We have placed a screen in a tray filled with water. And because the screen has a wooden frame, it will float. So it is easier. At times, some labs use a metal frame screen. So then you have to adjust the level of water till the level of the screen. Another one is blotter wash. Here we wet the blotter and put the paper over it, and we'll find this all the acidic components, and whatever can be absorbed by water, dissolved by water, is taken up by the blotter. Then paraprint washing. Another one is gel, like I mentioned, gallon gum. It can be used as a local treatment as well as for the complete paper object. So here I have taken a sheet of gallon gum, a gel of gallon gum, and I've placed the paper and covered it with mylar. And after some time, you can see that most of the acidic components, and even there were some reddish stains of some dye or ink, they have also come off. So gallon gum is actually, as far as agarose is concerned, it doesn't. It also needs heating. Xanthan gum doesn't need heating. You can just mix it with water. Gallon gum needs exactly 80 degrees Celsius with continuous stirring for 10 minutes. And then you can pour it in a petri dish or a tray. If you want small amounts, plugs, then you can use petri dish or you can use a tray, and you can form a thick gel like a sheet of gallon gum gel. Now, all these things that we have just gone through, the cleaning properties of water in case of oil paintings, wall paintings, and water and paper paintings, they're all using one main property of water, which is it's being a universal solvent. Why is water called a universal solvent? Now, this is because it is the only solvent, it is rather that can dissolve or maximum number of material. And so no other solvent can dissolve or so many different kinds of material. And so it is called a universal solvent. It is capable of dissolving more substances than any other liquid. So I would like to mention these few points before I go further, and I'll be talking about all of them. First thing is, water is an unusual hydride. It is a hydride of oxygen, H2O. And if we look into the properties of other hydrides, it is quite unusual. Its intermolecular bonding is much more than would have been expected. And hydrogen bonding is there in water, which is causing this intermolecular attraction and stronger intermolecular forces, bonds. And because of this hydrogen bonding only, there are many things that we can talk about, like even in paper, the paper relaxes because of this hydrogen bonding, and how it happens we'll talk about in some other session. Another thing is solvent power of water. What exactly we mean by the solvent power of water, we'll see in the coming slides. Then we'll talk about the dissociation of water, how water molecule dissociates, and dissociating effects of water, how it dissociates things added to it, and how it will help in our conservation lab. Let's see. So water is an unusual hydride because of its hydrogen bonding. It has solvent power. It is a universal solvent. Then it dissociates when in pure form also. And it has dissociating effects on other substances added to it. Now, water, a hydride with unusual properties. Here, I would just these are the charts of enthalpy or heat of vaporization on the right, and the boiling point on the left. They are quite, the boiling point and enthalpy of vaporization is directly proportional. They are similar, but there are some differences which we won't be talking about here. Here, I would just like to mention this. This is water. And as we see, as we go from left to right in the periodic table, we see that the general trend is that as the atomic number is increasing, the number of electrons per molecule is also increasing. Hydrogen is same. It is these are all hydrides, and there is some other element. So here it is H2O, it is water, it can be HF. And so as we move right in the periodic table, the enthalpy of vaporization increases. Means it takes more energy to break the intermolecular forces, and the boiling point will increase. According to this trend, water are all these first period elements, these period elements should have a lower boiling point. But the first element in each group is unusual because it is very small. So the intermolecular attractions are somehow much larger than expected. And this trend also, if we see here in these two groups, it is much greater than the first and the next one, but water is much more than even these two. So it has this uniquely strong degree of interaction among its molecules. Similar is the chart for the boiling point. And here, it's just a kind of reminder of the periodic table of the elements of what all of us and the whole life and living, non-living, everything, the universe is made of these types of atoms. So these are the elements. We won't talk about everything. I'll just would like to focus on these first two groups and these last ones. These are metals because they have one or two extra electrons in their outermost shell, which they want to get rid of, they want to give, donate. And uh, these ones, last two and horizontally like this, these are, they have one or two electrons, one, two, or three electrons less than the stable configuration of 8. So they want to gain one, two, or three electrons. So when they gain electrons, they become electronegative. These, when they donate, they become electropositive. So if they are around each other, they'll become oppositely charged, and they form ionic compounds, ionic bonds. But if a molecule is being formed among these molecules only, for example, hydrogen, H2, so it can not give, both of them don't want to take electrons, so they share electrons to get the stable configuration. Similarly, over here, if we take chlorine gas, none of them want to get give electrons, so they share electrons. So here why I'm talking about all this is we're talking about water basically, is because generally we'll be talking about the bonding in water within water molecule and with other water molecules, intermolecular forces. So for that, we must know the basic types of bonds. So we have two types of bonds: ionic bonds, where one atom is donating the electron and another one is accepting the electron. And another type is covalent bonding, where two atoms are sharing this pair of electron. One electron is from this fluorine atom, left fluorine atom, and one electron is from the right fluorine atom. So these are the basic bonds in most of the molecules. Coming to the covalent bonds. Covalent bonds they can be, because they're sharing, but still at times when the two atoms that are sharing a pair of electrons, their electronegativity is quite different, and one is more electronegative than the other, then this sharing is not equal. The electron might be more towards the more electronegative atom. So such covalent bonds are called polar covalent bonds. So a covalent bond in which bonding electrons are shared equally between the two atoms are non-polar covalent bonds, and polar covalent bonds are those in which the atoms have an unequal attraction for electrons, and so the sharing is unequal. Let's talk about water, coming back to water now. So water has two covalent bonds, which are polar. You can see the oxygen atom, 2 electrons in the inner shell and 6 in the outer shell. The stable configuration is 8, so it needs 2 more. Hydrogen is not giving 1 electron. They're not giving their 1 electron each. Rather, they are sharing in this particular case. So it is a covalent bond. But since oxygen is highly electronegative, the electron pair, this pair, is more towards oxygen as compared to the hydrogen. So it is a polar covalent bond, and this portion acquires a delta negative charge, and this portion acquires delta positive charge. Now, this again is not that simple. There are other molecules which have similar polar covalent bonds, but they are not polar. Let's go back to the earlier slide. So water has polar covalent bonds, and hence it is polar. It is not just because of these polar covalent bonds that it is polar. I want to make this point. There is more to it. There are 2 lone pairs which are repelling, and so the shape of the water molecule is bent. It is like this. And this is also contributing to the polarity of the water molecule. Here you'll see 3 molecules: water, methane, and carbon dioxide. Water has 2 polar covalent bonds, and two lone pairs are also present on oxygen, and its shape is bent. So it is polar. Uh, the area where hydrogen atoms are there, it is positive, and the oxygen atom area is delta negative. So there's a polarity. Methane has non-polar covalent bonds, four of them, and the whole molecule is non-polar. So polar covalent bond of water is polar covalent bonds are forming polar molecule, four non-polar covalent bonds in methane. They result in non-polar molecule of methane. But carbon dioxide, it has polar covalent bonds, two of them, just like water. But there is no lone pair on the carbon, and the shape is not bent. And it is a linear molecule. So it is nullified. If here the electrons are moving towards left, in this bond, they're moving towards right. So they are nullifying the effect. So both sides are, you can say, negative, if you want to call that negative. So there are no opposite poles. So it is a non-polar compound or molecule. So this is something interesting, that water has polar covalent bonds. It has a bent structure, and hence it is a polar molecule, a very small polar molecule. And because of this whole thing, this shape and this polarity, hydrogen bonds are formed between hydrogen and this oxygen, which is highly electronegative. So this is, hydrogen is positive, so it is in this molecule, but this sharing is happening, and this is a covalent bond. So another attraction with this, another oxygen atom of another water molecule exists, which is quite strong, but not as strong as the intramolecular hydrogen-oxygen covalent bond. So this kind of bond, intermolecular bond, intermolecular attraction between hydrogen and a highly electronegative atom. Here it is oxygen, it can be fluorine or nitrogen, is called a hydrogen bond. And these bonds are weak when they are compared to the truly covalent intramolecular bonds. So this hydrogen bond can be formed with any highly electronegative atom in another molecule. So it is an intermolecular bond. It can be fluorine, nitrogen, or oxygen. The solvent power of water. Water is known as a universal solvent. We have already mentioned. Water is an excellent solvent for compounds ranging from uncharged organic compounds like oils are not miscible. They are not miscible in water. So, or we can say any of the hydrocarbon like butane, pentane, methane. So hydrocarbons are, so water is an excellent solvent for compounds ranging from uncharged organic compounds like methane, butane, to salts that are completely dissociated into ions like sodium chloride. Even in solid crystalline state, they have different ions. Now let's see how this is happening. So ranging from the uncharged organic compounds to the salts, which are dissociated even in their solid form. Hydrocarbons are notoriously insoluble in water, but as soon as one substitutes a hydroxyl group, one forms an alcohol, which is more soluble in water. So if we see that methane is, or another alkane is insoluble in water, if any one of this hydrogen is replaced by hydroxyl group, it will become an alcohol. And alcohol, because of this oxygen, electronegative oxygen, will impart some certain level of polarity and would be more soluble in water. So this is because of the proton of this hydroxyl group, H positive, forms the hydrogen bond with the oxygen atom of the water. So if there is water, so a hydrogen bond would be formed and it would be miscible. Now, so water is an excellent solvent because it not only dissolves the salts, which are polar, but also dissolves organic compounds, which can become polar if they gain a hydroxyl group or carboxylic group or keto group, which incorporate oxygen, or even amino group which has nitrogen. Now the rule is like dissolves like. Polar solvents like water would dissolve all polar compounds like salts, but water also dissolves many organic compounds with the functional groups like hydroxyl, carboxylic acid, ketone, amino, etc., which have little or more polarity because of the highly electronegative elements like oxygen and nitrogen. The dissociation, our next topic was dissociation of water. Water does not only act as a solvent for other charged substances, but it itself is capable of dissociating to a slight degree in the following manner. Here you can see a water molecule is breaking into H positive and OH negative. So in itself, even in pure water form, some of the molecules dissociate. But this is very not very frequent, like only 1 in, say, 10 million molecules of water would dissociate. But whatever amount, it is important for us. And another thing to see over here is this hydrogen ion. It is too small. I'll just talk about it in the next slide. And it cannot exist as such. So it is readily absorbed by, so this is one water molecule and this is another one, hydrogen bond. So it is readily absorbed by the other water molecule to form a hydronium ion. And OH is left. So hydrogen ions do not exist as such because there are plenty of water molecules. They join another water molecule to form a hydronium ion. So this is just a diagram because in reality, proton is not that big. Hydrogen is just one proton and one electron revolving around the proton. So it is too small. Let's see in the next diagram. So this is just a pictorial depiction of what the reaction that we saw earlier. This hydrogen is too small, hydrogen ion. So it is sucked in by this electronegative oxygen. And one of the lone pair, the oxygen shares with that hydrogen. That is just one proton. And just one lone pair is left. So this particular ion, H3O positive, is called hydronium ion. So whenever we are talking about hydrogen ion, actually we are talking about hydronium ion. So even if in reactions it is written as H positive, it is actually H3O positive. So water dissociates, and as such, it is forming H positive and OH negative ions. Anything that releases H positive ions is an acid, and which releases OH negative ions is a base. So water acts both as acid and a base. It is weak acid and a weak base. I should have written weak. The adjective should also have been mentioned in this slide. So this was about water, pure water. Some of the molecules, though not very frequent, 1 in 10 million or 1 in, I think, 550 million, dissociates. But it also dissociates, enhances the dissociation of other substances. The strong electrolytes like sodium chloride, they are dissociated, they are in their ionic form, even in their solid state. But there are certain electrolytes which are weak, and as such, they are not in their ionic form. They are in the molecular form. But when they are put in water, some of just a portion of them, it dissociates. So besides being capable itself of dissociating, water is able to enhance the dissociation of other substances, which we call weak electrolytes, because in pure form, they occur largely in undissociated form and more dissociate as they are increasingly diluted in water. So for example, a weak acid such as acetic acid, 2-carbon acids, COOH group, experiences the following equilibrium. So it is reversible, it is in equilibrium. This is something important to remember, and that is what we are using in conservation practice. We are using this reversible nature of weak acids in water. What we see here is that this acid is releasing H positive, which is joining with the water to form hydronium ion. So some of the acetic acid molecules break in these two ions, but many of these ionic forms would go back to the molecular form. So there is an equilibrium. And how much of a weak electrolyte would turn into the ionic or the dissociated form depends upon the molecule, different molecules, and temperature and pressure. So if we just forget about temperature and pressure and we just think about that these reactions are happening at 25 degrees Celsius, room temperature, then we can focus on the other things. Another thing is the concentration. So we'll just see in next slides how it happens. So this is acetic acid. When we put it in water, it dissociates. Not all the acetic acid molecules are dissociating. This we have to remember. Most of them are in the molecular form, and some of them are in this form. So the reaction is happening both forward and backward. There's a delicate balance. And here we can see that water is actually competing. It is trying to pull this hydrogen ion to form a hydronium ion. Now, before I go further and talk about this reversible reaction and how we are using it in our conservation lab, I would just like to remind everybody the difference between strong acid and weak acid. So strong acids, when an acid dissolves in water, a proton is transferred to water molecule to produce a hydroxyl ion, and negative ion depending on what acid you're starting from. So if we take the acid as A, so it has hydrogen. So the acid is HA. We put it in water, hydronium ion is formed by release of this hydrogen, and A negative is left. It is a conjugate base of the acid HA. So this happens to all the molecules of the acid. So a strong acid is one which is virtually 100% ionized in solution. When we put a strong acid in water, all the acid molecules are dissociated into hydronium ion and the conjugate base of the acid. Once the hydrogen is released from the acid, it becomes its conjugate base, because now it will try to take the proton. It is negative now, so it has become basic. So strong acids are those which are completely 100% ionized in the solution. Weak acid is one which doesn't ionize fully when it is dissolved in water. For example, ethanoic acid. which is also called acetic acid. We just saw it in another slide. When it is put in water, some of the ions, only about 1% of ethanoic acid molecules have converted into ions. The rest remain as simple ethanoic acid molecules or acetic acid molecules. Most organic acids are weak acids. Similarly, strong base is something like sodium hydroxide or potassium. So here you can see the reaction is just in forward direction. All the sodium hydroxide molecules, they will dissociate to sodium ions and hydroxide ions. So a strong base is something like sodium hydroxide or potassium hydroxide, which is fully ionic. You can think of a compound as being 100% split up into metal ions and hydroxide ions in solution. Each mole of sodium hydroxide dissolves to give 1 mole of hydroxide ions in the solution. Weak base. Ammonia is a typical weak base. Ammonia itself obviously doesn't contain hydroxide ions. It doesn't have OH negative ions. It cannot release OH negative ion from itself, but it reacts with water to produce ammonium ion and hydroxide ion. However, the reaction is reversible, and at any one time, about 99% of ammonia is still present as ammonia molecule. Only about 1% has actually produced hydroxide ions. A weak base is one which doesn't convert fully into hydroxide ions in a solution. Another thing about acids and bases is the pH scale. pH scale is inversely related to the hydrogen ion concentration, which means that lower the pH, higher the hydrogen ion concentration. This is a very interesting topic, but it needs a separate 1 hour thing. So lower pH means higher hydrogen ion concentration, and higher pH means lower hydrogen ion concentration. By raising the pH, this is something important that we use in our lab. By raising the pH, many components that are weakly acidic can be easily removed from the surface. So this is what we did in our earlier slides when I mentioned a canvas painting where I was removing grime. And even in one painting, the old aged varnish was removed by simply raising the pH. Because the varnish had oxidized over time, the long chain molecules had been broken down and they had been oxidized. So it has become, the acidic groups have been added, and it has become acidic, more weakly acidic though, because it is an organic chain which is getting acidic. So it is a weak acid, and just by raising the pH, let's see if I have this in our, it is in the next slide, I think, how it happens. No, I'll have to explain in this one. I hope this equation is visible, because it's not visible to me because of a bar from Zoom. So here I have taken the acid as BH. B is some compound. I have taken it B because once it is, it has donated its hydrogen, it will become a conjugate base. So if we have a weak acid, which is suppose BH, and water is added to it, it will form B negative and H3O positive. Here, the reaction is reversible. Now, if we want the reaction to happen in the forward direction, like if we want this weak acid to break, what can we do? Why is raising the pH helping in breaking this weak acid? We'll talk about 2 laws. The law of mass action, which states that when a system reaches equilibrium, the ratio of the products like this B negative and H3O positive, their concentration at a given temperature is always a constant. For different material, it is a different value, but it is always that value, that constant. Of course, if temperature is changed, this constant will change for that temperature. So it is a constant value. And BH and H2O is liquid, so its value is taken as 1. So it's not written in the denominator of this equation. You see, these are the products, H3O concentration and concentration of B negative, divided by concentration of the reactants. We have written BH concentration. This square bracket means concentration. And concentration of water we haven't written because it is 1. So this ratio is always fixed. And another law, which is also called equilibrium law or Le Chatelier's law, it states that addition of reactants or products to a system at equilibrium. Now, if this equation is at equilibrium, this particular system where we have a weak acid and water, and it is dissociating, this is at equilibrium. But we want more of acid to go in this dissolved form. So if in a system at equilibrium is exposed to some kind of stress. Now here the stress means changing the concentration. This system is at equilibrium, the concentration of this, and the reactants is fixed. It's in a fixed ratio. But if we increase the concentration of suppose these hydronium ions, what would happen? The law states that it would then move. Right now it is in equilibrium, but then it will move towards right or left, depending upon what stress you have put. So if you have increased the concentration of hydronium ion, it will move in the direction where the stress is released. Means this extra hydronium ion that you are adding is removed. It will get removed in the backward direction. So here, if we increase the hydronium ion concentration, we decrease the pH because hydrogen ion concentration is inversely proportional to pH, then the reaction will go in the backward direction. But we want the reaction to go in the forward direction. We want to break this weak acid. So we increase the pH. That means we decrease the concentration of hydronium ion or hydrogen ion. If this is decreased, the system would move in the direction where it is made, so it is compensated. So reaction would move in the forward direction. So this is what happens when we are increasing the pH. Then we are decreasing this hydronium ion concentration. And this reaction with water of that weak acid is moving in the forward direction, and the weak acid would break. So this is about how we are using this chemistry in art conservation. There are many things. I'll just rush through the rest of the things. Apart from increasing the pH, we can add surfactants, which have hydrophobic and hydrophilic ends. So anything which is not soluble in water, oily thing, they'll form, suppose that grime or thing is over here. Let me change the color. So that grime is over here. So the hydrophobic tail would get attracted towards that grime, which is also hydrophobic. And all the surfactant molecules will align themselves like this around that hydrophobic thing with their tails towards the hydrophobic, because tail is hydrophobic. So like dissolves like. And ultimately a spherical thing is formed with the surface. On surface, you see there are blue balls. These are hydrophilic. So now the whole ball is hydrophilic. It is water loving and will be removed by water. And the hydrophobic grime is trapped inside. So we can, and we have done that in certain paintings, as I mentioned. We've used the surfactant also to remove the oily thing from the surface. Then enzymes. Enzymes are very specific, and we have been talking about them, and we can use them in certain cases where some oil is very stubborn and is not coming off with any of these things that we have mentioned. We can use a little amount of enzyme which acts in water again. a substrate or the long chain organic compound specific for that enzyme. Um, and the enzymes have a particular shape which fits in the substrate. Uh, it is exactly complementary to the substrate. It gets fit in the enzyme. The substrate gets fit in the enzyme, and there's a movement which causes the breakage of this substrate, and the products are released. So this is again very interesting. We can talk about it separately to treat certain things which are not being removed or cleared by the general procedures. We can use specific enzymes. Similarly, we can use chelating agents, as I mentioned in that picture with the white haze, the painting with the white haze. Most of its areas in the white haze were removed with the modified water, which included chelating agent. Like what I used was EDTA. And these are compounds which have structure which which takes the metal ions and form a water-soluble complex. And hence the metals ions can be removed very effectively with the help of chelating agents. I won't be talking about buffers. It's a long topic, and there are many more things that we could have discussed. You can see in the slides, but we'll talk about them some other time. Basically, I wanted to talk about the basic chemistry of water, its bonds, intermolecular bonds, intramolecular bonds, its shape, and how it is affecting its solvent property and its dissociation, and how it affects the weak electrolytes. And by these two laws, we can manipulate, because this is a reversible reaction. We can manipulate wherever we want the reaction to go, to forward or backward, by increasing or decreasing one of the products or reactants. And this is what is happening when we are increasing or decreasing the pH in our cleaning solutions. Thank you so much. That's all. And it would be really lovely if we can share our ideas, we can share our concerns about these procedures, and we can share our knowledge with each other. So I would really welcome any kind of questions or any suggestions, advice, everything regarding these water-based cleansing methods. Thank you so much.